Hi, good morning to one and all. I am KV Harish, Assistant Professor, Department of Civil Engineering, IIT Kanpur. You are watching MOOC lecture course on hydration, porosity and strength of cementitious material. Today we will see lecture 13, Portland cement based paste systems. The textbook and reference materials are shown here. So today's topics will be components of hydrated Portland cement based paste systems, mechanism of cement hydration, introduction to heat of hydration of PCBPS. This lecture will provide different compounds present in the hydrated cement paste. In addition, the mechanism of cement hydration, the importance of heat of hydration and how it can help to understand the hydration process is also discussed. Now, the first one is components of hydrated cement paste. So, typically the hydrated system contains several compounds or components. First one is calcium silicate hydrate gel, many times referred as tobermoride gel, calcium hydroxide. Remember that calcium silicate hydrate gel and calcium hydroxide primarily comes from the hydration of calcium silicates, that is tricalcium silicate and dicalcium silicate. The third one is ettringite and fourth one is monosulfoaluminates AFM, and remember that ettringite and monosulfoaluminates are hydrated products from tricalcium aluminate. And in addition to these four compounds, which are generally referred as major hydrated compounds, you also have some minor compounds. You also have unhydrated cement, which means of the entire cement that you have initially put in water may not fully hydrate. So, you may have in our PCBPS system that some cement grains are still not fully hydrated. You also have pores where you have capillary pores, gel pores, entrained air, entrapped air, and you may also have water filled in pores. Some pores may be completely empty, some pores may contain water. So, you may have water filled pores which are many times called as pore solution. In this lecture we will concentrate only on the first four components. The other four components will be covered at a later stage. Now, the four major compounds are listed, and what this table shows briefly is some of the important morphological properties or microstructural properties. So, usually you see specific gravity, it ranges from 2.3 to 2.6 for calcium silicate hydrate, calcium hydroxide somewhere about 2.24, ettringite 1.75 and monosulfoaluminates 1.95. If you carefully see, the ettringite and monosulfoaluminates have lower specific gravity primarily because the water content. If you see the formula for ettringite and monosulfoaluminates, you have more amounts of water. In the case of ettringite, it is H32. In the case of monosulfoaluminates, it is H12 to H16. So, the specific gravity of, since the specific gravity of water is 1, you generally find that ettringite and monosulfoaluminates have lower specific gravity compared to the CSH and calcium hydroxide. Now, from the point of crystallinity, what we see is that calcium silicate hydrate is explained to have very poor crystallinity, calcium hydroxide very good, ettringite good and monosulfoaluminates fairly good. In the case of morphology, that is, if you see at the micro level, because all these compounds are at the micro level, basically at the macro level we cannot see or understand the morphology. So, we need scanning electron microscope or TEM or optical microscope to understand how it actually looks at the micro level. So, in the case of calcium silicate hydrate, morphology is explained as spines or unresolved morphology. In the case of calcium hydroxide, non-porous striated material. In the case of ettringite, long slender prismatic needles. In the case of monosulfo-aluminates, thin hexagonal plate or irregular rosettes. We will see some of the scanning electron microscope images in the coming slides, and also approximate crystal dimensions are shown. As I already mentioned, these are at the micro level, and hence you see that these are approximately in the range of say 0.1 micron meter to about 10 micron meters. So, if you take calcium silicate hydride gel 1 cross 0.1 micron meter, calcium hydroxide is 0.01 to 0.1 mm, ettringite is 10 cross 0.5 micron meter, and monosulfo-aluminate is 1 cross 1 cross 0.1 micron meter. Now, if you see the scanning electron microscope images, calcium silicate hydride gel typically looks like this, and remember that in the table it is explained as spine or unresolved morphology, which means the morphology changes depending upon the situation that exists in the system. If you have more water, it may slightly change. If you have more temperature, it may change to other, and something like that. So, the next SEM figure shows at different stages morphology of calcium silicate hydride gel. So, when you add water to cement and when the system is very fresh, which is explained as wet, you see that the calcium silicate hydride gel looks like this. After say about 16 hours of drying, from the time water is added to cement, if you take a scanning electron microscope, this looks like this, and say after 2 weeks, typically 14 days, we see that calcium silicate hydride looks like spines. So, you can see that the morphology slowly changes. In addition to that, even this morphology is not completely fixed, in the sense that if temperature inside concrete changes substantially, then the water comes out of the system and this again slightly changes. The second one is morphology of calcium hydroxide, and it is explained as non-porous striated, and you also have hexagonal prism. So, these appear like hexagonal prisms, and it is non-porous and striated. And the third one is ettringite, where you see that you have prismatic needle like structure and which is long and slender. And in the fourth one you have monosulfo-aluminates, where you have the morphology looking pretty much like thin hexagonal plates, and what you see here is something like petals of rose flower. So, it is explained many times as irregular rosettes. Now, the second topic is mechanism of cement hydration. In mechanism of cement hydration, we have two proposed mechanisms. One is through solution hydration mechanism, the other one is topochemical or solid state hydration mechanism. We will see each of the mechanism in detail. Through solution hydration mechanism is perceived to be dominant the moment water is added to cement until some period between its initial and final setting time. So, which means through solution dominates when the mixture is relatively plastic, when the mixture is relatively wet, and what happens in through solution is that reorganization of constituents of the original compounds happen, dissolution of anhydrous compounds into its ionic constituents, formation of hydrates into the solution, eventual precipitation of hydrates from the supersaturated solution due to the low solubility of hydrates. So, three things happen, and in order to understand the dissolution process, what you have to know is that the tricalcium silicate dissociate into calcium 2 plus ions. Remember that in the morphology of the compounds we have already seen that they exist as calcium ions and silicate ions. So, tricalcium and dicalcium dissociate into calcium 2 plus ions and SiO2 minus ions. In the case of aluminates dissociate into calcium ions and AlO4 minus ions. Remember, you have 6 numbers. In the fourth one, you have tetracalcium aluminoferrite getting dissociated into calcium 2 plus ions and aluminium iron O4 ions or iron aluminium O6 ions, and you also have fifth compound gypsum dissociating into calcium ions and sulfate ions SO4 2 minus. And in addition to that, you also have minor compounds like alkalis, namely Na2O and K2O, which dissociate into Na plus and K plus ions. And remember that since water is present, since we are adding water to the system, water is also substantially present as H plus and OH minus ions, and in this case OH minus largely dominates. Now, formation of hydrates into solution. So, basically what you have to know is that in the previous slide we have seen that the compounds basically dissociate into respective ions, and we also have to know which ions are reactive, which ions are less faster in reaction. So, AlO4 minus ions, SO4 2 minus ion, sodium ions, potassium ions, calcium ions, these are very fast in reacting, and especially the aluminate and the sulfate ions are extremely fast. The ions which are relatively less faster are silicon ions SiO2 minus, AlFeO4, FeAlO6 ions. Now, so the first reaction that actually happens is the formation of AFT, which is ettringite, and this depends primarily on sulfate to aluminate ratio and in the previous lecture. So, AlO4 minus ion plus 3 SO4 2 minus ions plus 6 calcium ions in the presence of water. Remember that here aqueous AQ refers to aqueous, which means you have substantial OH minus ions and H plus ions, that gives ettringite. And remember that this reaction we have already seen it in the previous lecture. And likewise, the aluminate ions and sulfate ions in the presence of calcium can also give monosulfo aluminates. Now, what this figure shows is to understand step by step what happens with time. So, there are totally 6 different cases that are provided. In the first case, where wetting of surface and dissolution of ions happen, you can see here that you have Al, K plus, sulfate ions, OH minus ions, calcium. So, all the ions from the compounds just come out into solution, and in the second one what you see is that there is a formation of semi permeable calcium silicate hydrate coating, and you also have ettringite AFT that is formed. So, you see that in this layer you have this gel and AFT getting formed, and the remainder goes into solution. And in the third phase what you find is that slowly the calcium silicate hydrate gel grows, and it is explained as metastable with aqueous phase and formation of AFT needles. AFT is nothing but ettringite. So, we have seen that it is long slender needles, and remember that this entire stage 1, 2, 3 together happens within few seconds to about few minutes, and with time continued hydrolysis takes place, which is step 4, and you see that the calcium ions go into solution, and it goes to the fifth stage where it is explained as supersaturation in calcium ions and OH minus ions and precipitation of calcium silicate hydrate gel, calcium hydroxide and others. And in the sixth stage there is rapid formation of calcium silicate hydrate gel, and there is depletion of anhydrous material. So, what you find is that there are different stages right from 1 to 6, and what is happening within few seconds to within few minutes to within few hours. We will now head on to the topochemical hydration process. This mechanism is perceived to take place at later periods of hydration, that is after final setting time. Remember that in the case of topochemical, it is explained to take place from the time water is added to cement to its initial setting time or final setting time. So, in this case it is what is happening after final setting time. Reaction takes place directly at the surface of anhydrous cement compounds without the compounds going into solution. This is very important because the system will remain in the wet state only for some time, and hence the through solution mode can dominate only up to a certain point of time. After that, once some compounds are formed, then it is the topochemical mode which actually dominates. The hydration of residual cement particles may occur as solid state reactions. So, how do we have to understand? Two figures are shown here. One is what is happening during the first 10 hours, the other one is what is happening just before 24 hours and until 14 days. So, let us first go to the first figure. So, in this figure again you have three different cases. One is the unhydrated case or less hydrated case. The second one is approximately 10 minutes after adding water, and the third one is approximately 10 hours. This will actually explain each of the case during the first 10 hours. So, what you find in the first figure is that during the first few seconds or minutes, C3A reacts faster, whereas C4AF does not react. So, and C3S also does not react. So, C3A basically reacts and forms ettringite, which is actually shown in the second figure. FSS, which actually indicates C4AF, that also does not react, and C3S reacts. Next stage you find that the ettringite is already formed, which is needle shaped, and slowly the calcium silicate hydrate gel is formed, which means C3S starts hydrating and it basically forms a coat on the cement grain. So, what is shown in this diagram is just one cement grain particle, and the formation of this coat basically stops the water that is present in the outside of the cement grain to actually enter inside of the cement grain. And with time what happens is this gel slightly grows thicker and it completely restricts the free movement of water from outside to inside. So, this happens during the first 10 hours. Now, in the second, what you find is that approximately at 18 hours you find that AFT is shown as needles. You also have calcium silicate hydrate gel. You will also find that C4AF slowly starts reacting, and say between 1 to 3 days you will typically find all compounds reacting together at the same time, and at 14 days you see that the hydrated compounds become larger. Okay. So, what we can understand in the 14-day figure is that you have some portion of the cement grain that is unhydrated and some portion, this black color region, showing that the hydrated compounds are formed, and all these things happen as a solid state reaction, and water cannot completely get into the cement grain, and it can do only through process called. So, some of the important assumptions in cement hydration are as follows. The hydration of each compound takes place independently of the others. Compound interactions is not considered, that is, the formation of any hydration compound does not chemically react with other hydrated compounds, although the growth of one may physically affect the other in terms of volume changes. So, what does it mean is that when you have different compounds that are getting formed here, one compound will not chemically affect the other, but it can physically affect in terms of their presence. So now we are going to the third topic, which is introduction to heat of hydration of Portland cement based systems. The hydration of each compound takes place independently of the other. All hydration reactions are accompanied by the release of heat. Heat of hydration at any time, HT, is a measure of the amount of heat evolved or heat energy for unit mass of anhydrous compound that has reacted, and it is many times expressed in joules per gram or joules per mole of cement. HT is also referred many times as enthalpy of the reaction, expressed in kilojoules per mole. Heat energy liberated by these individual compounds are already known and available. From the values or trends obtained from heat of hydration of the system, more information about chemical reactions can be obtained. Now, what is the importance of heat of hydration? Heat of hydration is important from three different angles. Number 1, total heat energy. Number 2, temperature. Number 3, rate of heat evolved. Total heat energy is important from the standpoint of knowing the development of properties with time. Temperature is important from the standpoint of thermal cracking, and rate of heat evolved is important from the standpoint of understanding chemical reactions that happen in Portland cement. Total heat energy, rate of heat evolved and temperature during hydration has relevance. Total heat energy from development of strength, rate of heat evolved from chemical reactions, temperature from thermal cracking. Total heat energy evolved is approximately 50% of the total heat energy evolved within 1 to 3 days, and it is also approximately 75% at 7 days, and the same value is approximately 83 to 91% at 180 days. Temperature of mixture can increase from 27 degrees Celsius to as high as 60 degrees Celsius depending upon the amount of cement content present and several other factors. During normal concrete operation, the heat is dissipated into the soil or air, and hence the temperature changes within the structure are not significantly high. Rate of heat evolved is nothing but heat evolved with time, that is, rate of heat evolution dHT divided by dt is related to many parameters including cement composition, fineness, cement content, casting temperature and many others. Just revisiting the slide that we saw in the previous lecture regarding reactivity of clinker compounds, these 4 compounds have different reactivity. And in terms of heat of hydration of cement compounds, we see that each and every reaction produces its own heat energy, and in this table you have the reactions given in this column, pure compounds given in this column, impure compounds given in this column, and cement as a whole is given in this column. And you find that in pure compounds, heat of energy can be measured in 2 different ways. One is calculated, the other one is measured. Calculated refers to using some mathematical equations, and measured is using calorimetry. Now, for the first reaction, which is reaction tricalcium silicate reactions, we find that this is approximately 380 joules per gram, and remember that here we have assumed that complete hydration takes place. In real, complete hydration does not take place, but we take a hypothetical situation that if 100% of the cement grains are hydrated, then approximately 380 joules per kg of heat is evolved from merely this reaction, hydration of tricalcium silicate. Likewise, if you see for C2S it is 170, C3A it is 1160, extremely high, and again individually for different hydrated compounds it is given, and if you take C4AF it is 420. You may have to compare this figure with the reactivity that is shown in the previous slide for understanding which is higher and which is lower. And likewise we also see that even in the measured case we have similar trends, but remember that the calculated and measured may not be necessarily same, but the trends that you get, for example, if you take the values of the heat values of the hydrated compounds of C3A, say 900, 1670 and 1150, these values are generally much higher than others, and that trend is also reflected in measured values. Now you may have to also compare what values you get for the pure cement compounds with that of what you get for the clinker compounds, and remember that pure compounds does not have impurities while clinker has impurities. So you see that the measured values of the pure compounds is approximately similar to the measured values for clinker compounds. So here it is 520, 570, 260, 260, 880, 840, 420, 335, somewhere lesser, and primarily some impurities can actually cause substantial changes to the heat of hydration. And likewise cement measured is also provided for comparison with the others. The next one is that what is the typical heat of hydration trend that we get. So if you take in the x axis ranging from 0 time 0 to say about 24 hours, and in the y axis let us first take the total heat which is represented as HT, denoted by continuous line. So what you find is that with increase in time the total heat slowly increases and then suddenly increases and then it flattens. Okay. The other graph which is heat rate dH by dt is shown by the dotted line. So what you find is that at the initial stage rate of heat is extremely high and it suddenly comes down within few seconds, and for few minutes it does not fully react, stays for some time, and then slowly the reaction picks up and then again it reduces. Okay. And here the time is shown in 0 to 24 hour scale, and what you have to understand is that the chemical reactions have to be understood from the rate of hydration plot with respect to time, which is actually done in the next lecture. With this we come to the end of for this lecture, and what we have seen is morphology of hydrated compounds, mechanism of cement hydration, and introduction to heat of hydration of Portland cement based systems. Thank you.